So yeah, so don't tell Charity any of those things I told about you, okay? Because we're recording now. Alright, so let's get started. We're talking about normal distributions here. I'm going to ask for a good reader to read this. Shayla, yes, you got it? Awesome, go ahead.
The distribution of serum cholesterol levels in women 18 to 24 years of age is approximately normal with a mean of 185 and a standard deviation of 48. Levels above 200 require attention. Find the probability that a randomly selected woman from this population has a cholesterol level greater than 200. Round your answers to 4 decimal places if necessary. Include a correctly labeled and shaded sketch of the appropriate distribution to support your solution. Research identify the mean and standard deviation in your solution.
Whew, lots of instructions there. But yeah, basically all this is talking about is cholesterol levels. When it said serum, did anyone else think of Winter Soldier? Captain the Falcon. Anyone else following that? Alright, well let's go through and let's do this one, okay? So I'm going to draw a normal curve because I've been told they're normally distributed, right? What is the mean of this normal distribution? And what is the standard deviation? So I'm going to draw a normal curve, and mine are never like perfect, but there we go. That's actually better than normal. Okay? Now, I'm going to put an N. What does N stand for? The capital N stands for normal, okay? And then I'm going to put a 185 and a 48. This is how I say this is a normal curve with a mean of 185 and a standard deviation of 48. Look good? Now, what was the question they asked? We want to find the probability of what? Greater than 200. So 200, I'm just going to guesstimate 200 is right about here. We don't know exactly, but that's okay. Now I'm going to show you both ways that you could do this problem here. Number one is that I'm going to say, hey, I'm going to find that probability using norm CDF. What I would ask from you is you say what the lower bound is and what the upper bound is. So if I were to put this into my calculator, menu 652, I believe, what do I push? Well, what do I say the lower bound is? And what's the upper bound? Okay, now notice I'm following the instructions. They want a correctly labeled and shaded sketch. Notice I should put something on here like cholesterol levels, sure, okay? But I've told them it's normal. I said the mean and standard deviation. There we go. Okay, so I'm going to get out my calculator. What buttons do we push for this one? Menu 6, 5, 2. And the lower bound we said was 200. Upper bound is 9999999. And for this one, I have to do the mean. What did we say it was? 185. And what was the standard deviation? Cool, I put all that in, and I get 37.7. They said round to 4 decimals, so I'm going to do 0.337. Wait, 0.3773, I said that wrong. 0.3773. So that's going to be the answer, and if this was a free response, I would recommend writing out a sentence saying the probability that a randomly selected woman from this population has a cholesterol level greater than 200 is 0.3773. Now, let's say you don't like norm CDF and you want to do things old school style. How would we do this? Well, we would need to figure out the z-score. To do the z-score, we take our number of interest, which is 200. We're going to subtract that from the mean and divide by the standard deviation. Remember, this formula is on your formula sheet. So I'm going to go 200 minus 185. Make sure you find that difference first. It's 15. Then divide by 48. And I get the z-score of 0.3125. Now I want to pause there and ask you guys, how do we interpret z-score? What does this 0.3125 tell us about 200? Take a second, turn to your neighbor, see if you can remember how to interpret that correctly. Alright, who can tell me, who feels confident that they know what that 0.3125 means?
Oh, no.
Go ahead, Emily. What does that 0.3125 tell me?
I don't know, but is it like how far away that is from
How many
standard deviation?
standard deviations we are from the mean? So the cholesterol level 200 is 0.3125 standard deviations above the mean. Okay, so it's pretty close to the mean. It's not even half a standard deviation away. So then what that means, if I go to my standard normal curve, which is going to be centered at 0 and has a standard deviation of 1. So I'm going to label this normal, standard deviation of, or mean of 0, standard deviation of 1. And I was to go to 0.3125, it's going to be in the same spot that 200 was on our other curve. Now to find this area, this is where you're going to go to that table, and you should get something that's about the same as 0.3773. So I'm going to borrow your table, Lacey, is that okay? So I'm going to come down here, it gives me the z-score, it gives me the tenths digit, and then I go across for the hundredth digit. So I'm going to, let's just say 0.313, we'll round up. So I'm going 3 point, nope, actually, I messed myself. I'm going to go to 0.31, that's it. So I go to 0.3, and then I go over to 1, and I get 0.6217. Now that 0.6217 is to the left, So I have to do, good job, 1 minus that, and I should get something close to this. It's not going to be exact because we had to do some rounding, but it will be close. This is how people used to do it before they had calculators. Now we have calculators, so you don't really need to do it, but if you want to, then fine, you can do it that way. Do you have any questions on that question? Alright, now this is when they give you a problem and say, what's the percentage for given this cholesterol level? The opposite is if they would say, hey, which cholesterol level would represent this percentage of data? When we're working backwards like that, which function do you use? Inverse norm, great job. Let's do a problem where we're going to see that. Okay? Let's have another reader here. Michelle, do you mind reading that one?
The manager of an In-N-Out Burger determined that the wait times in the drive-thru were normally distributed of 2.3 minutes with a standard deviation of 0.42. What is the probability that a customer's wait time is greater than 2.9 minutes, including approximate wait label schedule for distribution?
Okay, I don't think that's true. Because anyone who's waited at In-N-Out, no, you're not moving in and out. It's kind of like you're just waiting. Now, this one is going to start out just like this, okay? So what I want you guys to do, draw a picture, label it, and find the probability that the wait time is greater than 2.9 minutes. Okay? And then I'm going to ask you a follow-up question. We're going to use inverse norm. So, draw a picture. Try to do those same thing. Let's see if we can agree on the same answer. I'll give you about a minute or two here.
It's the same as so first you say the minutes and then it says great. So the first you just greater than it's like up there. It's greater than 2.9. That question. That's the mean. And then just try out
Alright, Quad, tell me how you drew this picture. What is it going to look like?
So I didn't draw the picture.
Boo. You need a picture.
I plugged it right into my calculator. But on
and down by, or up from 2.3 by 0.42 and down by 0.42.
Yes.
That's what you're saying, right?
Yes.
Awesome, and then what are we asking in this question?
We're trying to find how many or the percentage of people that has a wait time of more than 2.9 minutes. So it's towards the right,
Good job,
and it's shaded on the right.
good job. So, did you do this using table A or norm CDF?
I use norm CDF.
That's what I would recommend. Okay, so cool. If we do that, then the lower bound is 2.9, and the upper bound is going to be 9999999. And what did you get that area was? Spot? Do you have it already? Or that? What is the probability of randomly selecting a wait time?
0.0766 or almost 7.66%.
What do you guys think? Does that match what you came up with? Awesome. That's how you do norm CDF. Now, if you're wondering, do you guys know how to do norm CDF if you've got a TI-84 or a TI-83?
Yeah.
Good. So it's second vars, okay? You go to second distributions, and then it's right there. So it's just second vars. If you need me to show you that, remind me and I'll show it then. Okay, but I'm going to ask a different question. Let's say I wanted to know what percent, how do I phrase it? Which wait time here would represent the, let's say, 60th percentile, okay? What I mean by that, let me draw a different picture, is if I were to draw this same normal curve, so same curve, it's still centered at 2.3 with a standard deviation of 0.42, so 2.3 is right there. I want to know which wait time would put 60% of the data to the left, and that means, or I'm going to write it as 0.6 to the left and 0.4 to the right. So this one is a little bit different. I'm giving you the percentage, or in other words, the probability, and I want you to come up with what is that wait time right there. So how are we going to do that? Inverse norm. Okay, let's do that. Everyone on your calculator, where do you find inverse norm? Ooh, good job. Menu 653. Now it's going to ask you for area. What does it mean by that? To the left. Good job. And when you're putting this in, we're writing it as a decimal. So even though it's 60 percentile, we want 60% to the left. How are we going to write that? 0.60. Nice job. So I'm going to go in here and put in 0.6. And then we'll update the mean and standard deviation. What was it again? 2.3? And then 0.42? Awesome. So then I'm going to push enter, and it gives me 2.41. We'll round that up to 1. So what that means is the wait time of 2.41 minutes represents our 60th percentile. That means 60% of the wait times are less than it, 40% are greater than it. Can you do inverse norm on your own? Do you have any questions? This is all we're going to do for chapter 7. You feel okay with that? Mm-hmm. Okay, cool. So that's chapter 7. The main thing you need to know, norm CDF and inverse norm. Okay, let's talk a little bit about chapter 8. I want you to turn to your neighbor and I want you to say, what is a sampling distribution? The whole chapter was on sampling distribution. So what is a sampling distribution? And then let's look over our formula sheet and find our key formula form, okay? So give you about 30 seconds there. What is the sampling distribution key formulas? Go. All right, let's come back in 3, 2, 1. You three right here. What did you guys say a sampling distribution was? beads are blue? There's 15,000 of them. Am I going to count all of them?
No.
No. So what I'm going to do instead is I'm going to take a sample here. Maybe. And there's 100 in there. So this is a sample of size 100. And I could say, okay, this percentage is blue. Cool. That's one sample. But if I'm doing a sampling distribution, I'm going to do all possible samples. So I do it again, and again, and again, until I've done it all possible times, okay? Let me show you an example. We've seen this visual before, but here's my distribution right here. I'm going to take a sample of size 5. And this is going to be sample means. So I did 5 randomly selected observations from this population, and I averaged it out to there. So this is one sample mean. Then I say, let's do it again. There's another sample mean, and then I do it again, and again, and again. And what I'm starting to see is, when I look at this is a collection of sample means. But this is only, I've done this about 200 times now. But you start to see patterns as you do this. What is the biggest pattern you need? There's 2 big patterns here that you should notice. What are they? So, yeah, so this was normal to begin with. So its sampling distribution was also normal. That's one of them. If it starts out normal, then absolutely the sampling distribution is normal. This is our population sampling distribution. This is our sample data. Okay, what's the other observation we should be able to make here? The mean stays the same. Awesome. So our means line up. So sampling distribution, all possible samples will have the same shape. If it's normal, then this is going to be the same shape. But notice it's a lot skinnier here. Okay, it's a lot skinnier. What if this is not normal to begin with? What shape will our sampling distribution make? Kind of depends, right? Could it be normal? If what?
30 samples.
Well, it's not necessarily the number of samples, because the sampling distribution is all possible samples, but it's your sample size. What is our cutoff for sample size? 30. What do we call that?
The
Central limit theorem. Good job. The central limit theorem says, regardless of the shape of our population, if our sample size is large enough, which we usually say 30 is large enough, then our sampling distribution is approximately normal. Let me just show you that. I think I've shown you this before, but let's just do it again because it's been a while. Let's change this to a skewed distribution. If I do a sample of size 2, sampling distribution of size 2, what shape is a sampling distribution? It was skewed to begin with and still skewed because our sample size was small. Even if I go up to 5, it's still skewed. But notice as I get to like 16, is that looking more normal-ish? If I go up to 25, that looks pretty darn normal, right? Okay, this is the main idea behind sampling distributions is you take all possible samples, and then we know some things about the shape as well as the spread and the standard deviation. So let's go over those key formulas real quick. Let's start with proportions. There's a little section in your formula sheet for this, right? Is there a sampling distribution section? We should, let's find this. Mu sub p hat is equal to what? P. You see that in your formula sheet? That just says the mean of your sampling distribution of your sample proportions will be at the mean of your the population proportion, okay? So the centers line up. Awesome. Then we'll see this one, the standard deviation of the sampling distribution of your sample proportions is P1 minus P over N. Right? See that there? Then lastly, what about the shape? Well, the shape will be approximately normal if, remember what our condition is?
and P1 minus P over 10.
That's our normal condition. So the shape will be approximately normal if we've met that condition. Okay, this is if we're dealing with proportions, or in other words, qualitative data. I have to think sometimes to make sure I don't say the wrong one. If we're talking about means, the formulas are just a little bit different, but still very similar. We're going to say the the mean of the sampling distribution of our sample means is mu. The standard deviation of the sampling distribution of the sample means is sigma over the square root of n. And we just talked about this with the central limit theorem. Our sampling distribution will be approximately normal if what? What does our sample size need to be? At least 30. Okay? Now, let's see. Remember did we talk about our population needs to be less than 5% of the population? Or sample size needs to be less than 5% of the population. So I'm going to add a little rule here. We've got, in order to use these formulas, we need to use the 5% rule. So it's kind of like a little fine print there. Always check 5%. Make sure your sample size isn't too big. So you want it to be big, but not too big, okay? And I could go into why, but it might be confusing. So we just won't talk about it. Okay. Are we good with those formulas? Do you have to memorize those? No, they're on your formula sheet, right? But what we're going to do is talk about how to implement them. So now let's go to the sampling distribution practice problems. It was one of your papers right here. Looks like that, right? Okay. This is going to refer back to the cholesterol one we did, okay? So let's have a reader on this. Lacey, could you read this one for us, please? Okay, so we already did this question when we did a sample of 1, right? What's going to happen when we do a sample of 50? Are we going to be as likely to get extreme observations? Now, what's going to happen to our shape? If our original shape was normal like this, what is our sampling distribution going to do to it? Skinnies it up, right? Because now we're looking at a sample of 50. If we're doing a sample of 1, we can get those outliers or those people who are on the far edges, but if we're doing 50, they're going to tend to be closer on it. So let's switch this up a bit. Let's talk about our sampling distribution for a size of 50. What is going to be the mean of the set? First off, let me back up. Is this data, is it qualitative or quantitative? When we're looking at their cholesterol levels, is that qualitative or quantitative? Quantitative, is it numeric and it makes sense to take the average of it? Yes, so that means we're talking about means here, okay? So don't use the purple formulas for this one, we're going to use a green mean one. So the sampling distribution of our sample means is going to be centered at mu, which we already said was what? 185. But now the standard deviation of the sampling distribution of our sample means, we're going to do sigma over the square root of n. Sigma was given as 48, and the square root, what was our sample size? Okay, so I'm going to get out my calculator, and I'm going to do 48 over the square root of